Good morning. So today I am going to discuss about the molecular orbital theory, assuming that all of you have learned the valence bond theory. So the first question will come: why we should learn the molecular orbital theory, since valence bond theory can pretty explain the shape of the complex or molecules, can predict the hybridization. But there are certain things which cannot be explained by valence bond theory. So, like why oxygen is paramagnetic in nature, or why oxygen is triplet in the ground state, that cannot be explained by the valence bond theory. Or the magnetic behavior of the molecule cannot also be explained by the valence bond theory. So, we need to learn the molecular orbital theory, which is developed by Mulliken. So, in molecular orbital theory, we generally say this MOT, discovered by or developed by scientist Mulliken in 20th century. And he assumed that the electrons are not localized to particular an atom or a bond, rather it is delocalized over the entire molecule. So, before going to details about the molecular orbital theory, we need to learn how the molecular orbitals are generated. Normally, the molecular orbitals are generated from the linear combination of atomic orbitals, which means that we have to have two atomic orbitals, then we have the linear combination, and then molecular orbitals generated. So, to have the linear combination of atomic orbital, there are certain criteria, like the atomic orbitals should be in similar type of energy, so that they can linearly combine. So, based on the linear combination, there are different types of bonding in the molecular orbital. Suppose if I assume that a molecular orbital is designated as psi 1 or psi A for atom A and psi B for atom B, there are two possibilities. The molecular orbital psi AB can be psi A plus psi B, or it can be psi A minus psi B. So, when psi A plus psi B happens, we say that the constructive interference happens. So, pictorially, if I am going to describe, suppose I have the atomic orbital, let's say this is psi A and this is my psi B. So, the psi A, psi B must have the similar energy and similar phase, similar symmetry, so that the linear combination happen, and after the constructive interference, we have a molecular orbital which is psi A B. So, since we have the constructive interference happens between these two atomic orbital, we say this molecular orbital as bonding molecular orbital. But situation differs when my psi A and psi B, they have similar type of energy, but they have opposite phase, and then the positive interference will not be possible. Instead of destructive interference is possible. As a result, we have the resultant molecular orbital psi A B, which called anti-bonding orbitals. Anti-bonding orbitals. So, if you look at these two diagram, we can see in the bonding orbitals or bonding molecular orbitals, The resultant atomic orbitals, they have lower energy than the individual atomic orbitals. Whereas in the antibonding orbital, the resulting molecular orbital have higher in energy than individual atomic orbital. So now it is clear that if I have two atomic orbitals, psi A and psi B, then we should have two types of molecular orbitals. One is bonding and another is antibonding orbitals. But there are other different types of molecular orbitals like non-bonded molecular orbitals. That means that the atomic orbitals are not going to linearly combine, they are inert during the formation of the molecular orbital. So once we have this idea about the bonding orbitals and antibonding orbitals, we can actually predict the different types of molecular orbitals for complex molecule, and we can able to understand the bonding behavior inside the molecules, the magnetic behavior like the bond order, also the magnetism. So one by one we will come to see how molecular orbital theory can help us to predict those properties. So first, let us consider about the simple molecule hydrogen. So to draw any molecular orbital diagram, we need to follow certain rules or certain steps. First, we need to see what are the atoms present inside the molecule. Here this hydrogen molecule means two hydrogen atoms are there, and this is a homoatom molecule. So in both cases the atomic contribution would be same. And then we need to know what is the electronic configuration of the individual atoms. For hydrogen, we know this is 1s1, only one s electron is there. So 2s electron of two individual atoms, they will combine and they will form the molecular orbitals of hydrogen molecule. And then we need to draw two perpendicular lines for two hydrogen atoms. Let's say this is my first hydrogen and this is my second hydrogen, and these are energy bars, and from bottom to up the energy is going to increase, and then you have to place the individual atomic orbital. Let's say this is my 1s energy. Since this is a homoatomic molecule, the second 1s will be at the same place. Then we place the electron here. We have one s electron. For this hydrogen, we have one s electron. So now these two atomic orbitals, they will combine, linearly combine, and they will form the molecular orbitals of the hydrogen molecule. So earlier we have shown that when two atomic orbitals are there, there will be possibility to form the bonding and antibonding molecular orbital. And bonding orbital will always have the lower energy than the individual atomic orbital. So my bonding orbital will be placed below. That means they are energetically stable. And since this is one s, which is the s orbital, we know they are spherical in nature. The only possibilities of forming the bonding is the head-on overlap. So once the atomic orbital, they are forming the molecular orbital in the head-on fashion, we know sigma bonds are formed. So this is sigma, and since the sigma molecular orbitals or sigma bond is forming from the 1s, we can denote this is as 1s. Sigma 1s, which means this sigma bond is formed from the linear overlap of these two individual 1s orbital. So once sigma 1 is formed, that means the destructive interference between these two 1s orbital will form the antibonding orbital, and this antibonding orbital will have the higher energy than the individual atomic orbital. So I place this antibonding orbital here, and since this is also sigma, we denote this sigma star 1 is sigma star means this is the antibonding orbital. Now according to Pauli's principle, this particular each molecular orbital will have maximum 2 electrons. So this sigma on S will have 2 electrons and sigma star will be vacant. So while the atomic electronic configuration of hydrogen is 1s1, now the molecular electronic configuration of this H2 molecule will be sigma 1s2 sigma 1s star 0. And since these two molecular orbitals are formed from the linear combination of these two atomic orbitals, we can draw the line to show that the contribution from these two 1s atomic orbital forms the bonding and the antibonding molecular orbital. Now, what are the things we can predict from this molecular orbital diagram? First of all, the bond order. That means how these two hydrogen atoms they are connected with each other. So, how to calculate the bond order? Bond order calculation is equal to the number of bonding electrons minus number of antibonding electrons. That means number of bonding electrons here is 2, number of antibonding electrons is 0, it is divided by 2, so it is 1. So that means these two hydrogen atoms they are connected through a single bond to form the hydrogen molecule. Another parameter also we can know, the magnetic behavior. We know the magnetic property depends on the unpaired electron. So since there is no such unpaired electron, we can say hydrogen is diamagnetic in nature. Right? So the magnetic behavior calculation is equal to root over n into n plus 2 Bohr magnetar, where n is the number of unpaired electrons. So since in hydrogen molecule we don't have any unpaired electron, the magnetic property of hydrogen is 0, so that means it is diamagnetic in nature. Okay. So these are the things we can easily predict from the molecular orbital diagram. Now we can also predict the stability of the molecule. Whether a molecule is stable or not, that can also be described by this molecular orbital diagram. Now let us consider an example. Instead of hydrogen, we have, let's say, helium. I am asking the question whether this helium-2 molecule exists or not. Okay. So that means helium-2 means we have two helium atoms, He1 and He2. So we know helium, the electronic configuration is 1s2. That means we have 2 electrons here, and this helium also have 2 electrons. Now we have 4 electrons, 2 molecular orbital, 2 will be in the bonding and 2 will be in the antibonding. So that means the bond order of this helium-2 will be 2 minus 2 by 2, it will be 0. That means there is no bond exists between 2 helium atoms. That is why we can say that helium-2 molecule does not exist. So from the molecular orbital we can easily predict the stability of a molecule. Now come to the particular question. At the beginning I told that why oxygen is paramagnetic in nature or why oxygen is triplet in their ground state, that cannot be explained by the valence bond theory. So we need to have the molecular orbital theory to predict. So similar for from hydrogen, let's just say this oxygen, that means we have two oxygen atoms. Let us say this is O1, oxygen 1 and oxygen 2. We know the electronic configuration of oxygen is 1s2, 2s2, 2p4. So here we only consider this valence electron, not the core electron, because we know the core electrons are enough to form the chemical bond. The valence electron are responsible. So two energy bars will be there for two oxygen atom. Let us say this is my 2s. For this oxygen also we have 2s energy, and then my 2p, which has three sharp cells, px, py and pz. Let us say this is my px, this is my py, this is my pz. So now I place the electron here. I know I have 2s electron here and 4 p electrons here. Similarly, for this oxygen also I have 2s electron and 4 p electrons. Now since 2s, we have linear combination and we can have first bonding 2s, then my anti-bonding 2s, and these two are connected with each other. 4 2s electrons are there, so in bonding I can have sigma 2s and sigma star 2s. Now for the p orbital we can have two possibilities, because we already know the p orbitals are dumbbell shaped. That means if these two p orbitals are forming molecular orbital in a header fashion, then the sigma p orbital will form. This is sigma p, and if they form the molecular orbital by sine and overlap, then there will be pi orbitals. So let us assume that my pz orbital, they form the sigma orbital, sigma to pz, and rest of the orbital they are forming pi orbital. So similarly, for bonding pi orbital, we have the anti-bonding orbitals, and for sigma also we have the anti-bonding orbitals. This is sigma to pz, and this is pi to p, pi star to px, and pi star to py. So I have 4 orbitals. This is 4 p electrons. So total 8 electrons. So I can have 1, 2. So electrons will fill from the bottom. Lower energy orbital will fill first. Then my 2 pi orbitals, and then these 2 pi star. So now we need to answer the question why oxygen is paramagnetic in nature. Look at these 2 pi star orbitals. Here you have 2 unpaired electrons. Just because of this presence of these 2 unpaired electrons, your oxygen is paramagnetic in ground state. And also because of these 2 unpaired electrons, the oxygen is triplet in nature. How to determine that? We know the multiplicity is equal to this multiplicity is equal to 2s plus 1 rule, where s is the spin of the electron. Now since we have two unpaired electrons, 1 and 2, so total spin will be 1. So 1 half plus half 1. So 2 into 1 plus 1 is equal to 3. So oxygen is triplet in nature. So after drawing the molecular orbital diagram of oxygen, we can determine that the oxygen is parametric in nature and at the same time it is triplet in ground state. Okay. So what will be the bond order of oxygen? Now we have to find how many number of bonding electrons are there. So if I say this is 2, 4, 6, 8. I have 8 bonding electrons. How many anti-bonding electrons I have? I have 2, 3 and 4. 4 anti-bonding electrons divided by 2. So it will be 2. That means we have a double bond between two oxygen atoms, which form the oxygen molecule. Okay. So now from here we generally ask the question that why oxygen is parametric, explained through molecular orbital diagram, and also we can ask, explain the oxygen 2 plus has the higher bond order than the oxygen. Right? So why it is happening? If I consider oxygen plus, that means I have 1 electron less. So from this molecular orbital diagram, which electron will eject from the outermost shell? Here the outermost shell is this pi star 2px and pi star 2py. That means 1 electron from this antibonding will be ejected. So that means my number of unpaired number of electrons, antibonding electrons will be less. So bonding electron will remain same 8, antibonding electrons now 3. So it is going to 2.5. Similarly, if I have oxygen 2 minus, then I can ask the question why oxygen 2 minus has lower bond order than oxygen. Minus means I need 1 extra electron. So where this extra electron will come? Again in the outermost shell and in this pi star orbital 1 electron will come. So that means number of antibonding electron increases. So for oxygen 2 minus, the bonding electron remains same 8. And now the antibonding electron instead of 4 it becomes 5. So it becomes 1.5. So we used to ask the question, explain the bond order oxygen 2 plus greater than oxygen greater than oxygen 2 minus. Then you need to draw the molecular orbital diagram of oxygen first, and then depending on the situation you can add 1 electron, you can eject 1 electron, and then calculate the bond order and explain the question. Okay. So you can see that after drawing the molecular orbital, we can generally explain the bond order of a molecule, the magnetic behavior of a molecule, and the state of a molecule. Okay. So next class, I will discuss about the heteroatomic system. The procedure will be same, but because of the presence of heteroatom, the energy diagram will little bit different because of the different energy levels. Thank you.